What if I told you that the moon, our closest celestial neighbor, holds a place so perilous and mysterious that it defies explanation? A region where science, danger, and intrigue collide to create one of the most enigmatic stories in our solar system. Why is this location so hazardous? And what secrets does it hold that have eluded humanity for decades? For centuries, the moon has captured our imagination. From ancient myths to modern science, it has been a symbol of wonder and curiosity. But beneath its familiar glow lies a world of extremes. Imagine a place where the temperature shifts from searing heat to freezing cold within hours, where radiation levels are lethal, and where the silence is so profound it almost feels alive. This is not just any location, it is the most dangerous place on the moon. But what makes it truly fascinating isn't just the hostile environment, it's the mysteries that surround it. Unexplained signals, strange geological formations, and anomalies that challenge everything we think we know about the moon. Scientists have spent years trying to unlock the secrets of this region, but every answer seems to lead to more questions. Could this be a key to understanding the moon's ancient history? Does it hold resources critical to the future of space exploration? Or does it guard something even more profound, a clue about our solar system's origins? As the moon becomes humanity's next great frontier, these questions demand answers. To prepare for future lunar colonies and interplanetary missions, we must first confront the dangers and uncertainties of this place. To fully grasp its significance, we need to take a step back and explore the forces that shaped the moon itself. Born from a massive collision billions of years ago, the moon has been shaped by relentless impacts, extreme radiation, and the vacuum of space. Over millennia, these forces have carved out its unique landscape, including the region we'll explore today. But the moon's story isn't just about its surface. Its influence on Earth is profound. It controls our tides, stabilizes our planet's tilt, and may have played a role in the development of life. Yet, for all its familiarity, the moon remains a place of contradictions, simultaneously ancient and unknown, inviting and treacherous. In this journey, we'll uncover what makes this location so dangerous and why it's vital to our understanding of the moon and beyond. We'll hear from experts who have dedicated their lives to studying this enigmatic region. We'll explore the challenges of surviving and operating in such an extreme environment. And we'll confront the profound questions about humanity's place in the cosmos. What lies ahead is more than just a story of science and discovery. It's a tale of human resilience, curiosity, and the unyielding drive to uncover the unknown. So let's step into the darkness and explore the mysteries of the most dangerous place on the moon. The answers may surprise you. Let's begin. The moon's surface presents an unparalleled, otherworldly landscape. Without the presence of wind, water, or erosion, its features have remained untouched for billions of years, preserving a vivid record of its violent and dynamic history. This is a terrain that speaks to the raw, unfiltered processes of the universe, a landscape shaped by forces so immense, yet so alien to our earthly perspective. The surface of the moon can be divided into two main types of terrain: the Maria, or lunar seas, and the highlands. These two regions differ significantly in their appearance, origin, and characteristics. The Maria, named for their resemblance to seas when observed from Earth, are vast, dark plains that cover approximately 16% of the moon's surface. These smooth, basaltic regions were formed from ancient volcanic activity, creating wide expanses that stretch across the lunar surface. Unlike their rugged highland counterparts, the Maria present a smoother appearance, yet up close, they reveal a complex web of ridges, shallow depressions and cracks. The highlands, in stark contrast, are bright, rugged, and heavily cratered. These regions, also known as terrae, are composed primarily of anorthosite, a light-colored rock rich in plagioclase feldspar. The highlands are home to countless craters, evidence of the Moon's long history of meteorite impacts. With their irregular, elevated terrain, the highlands present one of the most challenging environments for exploration, requiring precise navigation to traverse safely. Adding to the Moon's distinctive appearance are the rays that extend outward from certain craters. These streaks of lighter material, composed of ejecta from impact events, radiate for hundreds of miles and give the Moon its striking visual texture. The Tycho crater, for instance, is one of the most famous examples of this phenomenon. Its bright rays, visible even to the naked eye from Earth, fan out in all directions, creating a stark contrast against the darker Maria. Another remarkable feature of the lunar surface is its extensive network of rills and valleys. These elongated depressions can take various forms, from sinuous rills that meander like ancient riverbeds to straight rills that appear as linear trenches. Sinuous rills, such as Schroeter's Valley, are thought to be remnants of ancient lava flows, their winding paths a testament to the Moon's volcanic past. Straight rills, on the other hand, are believed to result from tectonic activity, where the crust has fractured and sunk over time. One of the most mysterious aspects of the Moon's surface is its permanently shadowed regions, particularly near the poles. These areas are nestled within craters so deep that sunlight never reaches them. While their significance for water ice deposits will be addressed later, their stark contrast to the surrounding illuminated terrain adds an almost surreal quality to the lunar landscape. These shadows, combined with the brilliant white of the highlands and the dark expanse of the Maria, give the Moon its iconic appearance as seen from Earth. The Moon's terrain is also punctuated by dramatic cliffs and escarpments known as scarps. These features, formed by the Moon's cooling and contracting interior, can rise abruptly from the surface, creating sheer drops that stretch for miles. For future explorers, these scarps represent both an obstacle and an opportunity, offering potential insight into the Moon's geological evolution, while posing significant challenges for navigation. Adding to the surreal beauty of the Moon's surface are its vast plains of regolith, the fine, powdery dust that blankets nearly every inch of the terrain. Regolith is composed of shattered rock, dust, and particles from billions of years of impacts. While its challenges will be explored in later sections, it plays an integral role in shaping the Moon's unique surface, covering features large and small with a fine, ghostly layer. The interplay of light and shadow on the Moon's surface creates a dramatic and constantly shifting visual landscape. Without an atmosphere to diffuse sunlight, the boundaries between light and dark are razor-sharp. This stark contrast transforms craters into deep, black voids, while illuminating ridges and highlands with a radiant, almost ethereal glow. From the smooth expanses of the Maria to the jagged peaks of the highlands, the Moon's surface tells a story of creation, destruction, and timeless preservation. Each feature is a chapter in the Moon's history, offering glimpses into its ancient past and the forces that continue to shape it. This terrain, both challenging and mesmerizing, sets the stage for exploring the Moon's most dangerous and enigmatic places. The surface of the Moon is not merely a backdrop for human exploration. It is an active participant in the story of our universe. The Moon is a land of extremes. Without an atmosphere to regulate its environment, it becomes a place where the forces of nature act unchecked, creating some of the harshest conditions imaginable. Understanding these extremes is crucial to comprehending why certain regions of the Moon, Particularly its most dangerous areas are so hostile. One of the most defining features of the Moon's environment is its drastic temperature fluctuations. On Earth, our atmosphere acts as a thermal blanket, distributing heat and preventing sudden changes in temperature. The Moon, lacking this protective layer, experiences dramatic swings. During the lunar day, which lasts approximately 2 Earth weeks, temperatures soar to around 250 degrees Fahrenheit, 121 degrees Celsius. This intense heat can make the surface unbearable, causing equipment to overheat and materials to expand or degrade. Conversely, the lunar night plunges temperatures to an opposite extreme, dropping as low as negative 250 degrees Fahrenheit, or negative 157 degrees Celsius. These conditions not only freeze the surface, but also pose significant challenges for technology and exploration. Batteries can lose their efficiency, and systems designed to operate in high temperatures can malfunction in the freezing cold. The sheer range of temperatures, from extreme heat to intense cold, is one of the greatest challenges faced by lunar missions. Adding to these challenges is the Moon's lack of an atmosphere, which exposes its surface to unfiltered solar radiation. On Earth, the ozone layer absorbs much of the harmful ultraviolet radiation from the Sun. However, on the Moon, this protection is non-existent. As a result, solar radiation bombards the surface directly, making it hazardous for both astronauts and equipment. This exposure increases the risk of radiation sickness and long-term health effects, such as cancer, for anyone who spends extended time on the Moon. Beyond solar radiation, the Moon is also subject to cosmic rays, high-energy particles originating from beyond our solar system. These particles, traveling at nearly the speed of light, can penetrate deep into materials and living tissue, causing damage at the molecular level. The absence of a magnetic field on the Moon, which on Earth helps deflect such rays, leaves its surface fully exposed. This constant bombardment is not only dangerous for humans, but also accelerates the wear and tear on equipment. Dust storms may not exist on the Moon, but another danger lurks in the form of micrometeoroids. These tiny particles, often no larger than a grain of sand, travel at incredible speeds, up to tens of thousands of miles per hour. While small, their impact can be devastating, creating craters on the surface or damaging spacecraft and habitats. The lack of an atmosphere means there is nothing to slow these particles down, allowing them to strike with full force. Another challenge of the Moon's extreme environment is the constant vacuum. Without air pressure, materials and systems behave differently than they do on Earth. Fluids can boil at lower temperatures, and the vacuum can cause certain materials to outgas, leading to potential malfunctions in seals and other components. Human bodies, without the protection of a spacesuit, would also face catastrophic consequences in such an environment. The Moon's long days and nights further complicate exploration efforts. Each lunar day or night lasts about 14 Earth days, creating prolonged periods of light and darkness. During the day, the unrelenting sunlight can heat surfaces to unbearable temperatures. At night, the lack of sunlight plunges the surface into freezing darkness. Surviving these cycles requires advanced technology capable of adapting to the extended periods of heat and cold. In addition to temperature extremes, radiation and micrometeoroid impacts, the Moon's gravity poses its own set of challenges. At just 1/6 the strength of Earth's gravity, the reduced gravitational force affects movement, balance, and the operation of machinery. While the lower gravity can make it easier to lift objects, it also means that dust and debris are easily disturbed, creating a floating hazard that can damage equipment or pose risks to human health. The interplay of these extreme conditions is what makes the Moon so inhospitable. For astronauts, Survival depends on their suits and habitats, which must provide a stable internal environment, shielding them from radiation, maintaining pressure, and regulating temperature. For machines, the challenge lies in creating systems that can endure the relentless exposure to radiation, the constant risk of impacts, and the dramatic thermal fluctuations. Despite these challenges, the Moon's extreme environment also offers opportunities for scientific discovery. By studying how materials and living systems respond to such conditions, scientists can develop better technologies for future space exploration. Understanding these extremes also helps us learn more about how planets and moons without atmospheres evolve and what conditions might be like on other celestial bodies, such as Mercury or even exoplanets. The Moon's environment, as harsh as it is, serves as a testing ground for humanity's ability to adapt and thrive in the cosmos. As we push the boundaries of exploration, the lessons learned here will pave the way for future missions to Mars and beyond. But for now, these extremes remain a stark reminder of just how challenging and unforgiving the lunar surface can be. The Moon is not just a reflection of Earth's night sky, it is a world unto itself, where survival is a testament to human ingenuity and resilience. The Moon's surface is a testament to the relentless bombardment it has endured over billions of years. Without an atmosphere to shield it, the Moon has been exposed to countless meteoroids, ranging in size from tiny particles to massive asteroids. These impacts have not only shaped the Moon's appearance, but also created a dynamic and ever-evolving landscape filled with craters, basins, and debris. Understanding the role of meteoroids is crucial in comprehending why certain areas of the Moon are so hazardous. The most striking evidence of meteoroid impacts is the abundance of craters that dot the lunar surface. From the massive South Pole Aitken Basin, stretching over 1,600 miles in diameter, to smaller craters just a few feet wide, these features tell a story of constant collision. Unlike Earth, where erosion and vegetation can erase impact scars over time, the Moon's lack of weathering processes means that every impact is preserved, creating a permanent record of its history. The size and frequency of meteoroid impacts have varied over time. During the Moon's early history, roughly 4 billion years ago, it experienced a period known as the Late Heavy Bombardment. This era saw an extraordinary number of collisions with asteroids and comets, leaving behind some of the largest basins we see today. These ancient impacts not only shaped the Moon's surface, but also influenced its internal structure, with shock waves from collisions causing fractures and redistributions of material deep beneath the surface. One of the most dramatic outcomes of these impacts is the formation of multi-ringed basins. These structures, such as the Imbrium Basin, are created when a massive object strikes the Moon with enough force to cause the crust to rebound and form concentric rings around the impact site. These rings are often surrounded by vast plains of ejecta, material blasted out during the impact, which can extend for hundreds of miles. Ejecta play a critical role in shaping the lunar environment. When a meteoroid collides with the Moon, it sends material flying outward at high speeds, creating secondary craters as the debris falls back to the surface. This process contributes to the uneven and treacherous terrain that defines much of the Moon. For explorers, navigating these regions is a challenge, as the scattered debris can make the surface unstable and unpredictable. Another consequence of meteoroid impacts is the creation of lunar regolith, the fine, powdery dust that blankets the Moon's surface. Regolith is formed from the constant churning and pulverizing of surface materials by micrometeoroids. Over time, this layer has become increasingly compact, particularly in older regions of the Moon. While it plays a significant role in the Moon's appearance, regolith also presents challenges for exploration. Its sharp and abrasive nature can damage machinery and pose risks to astronauts if inhaled. Micrometeoroids, though small, are particularly dangerous because of their high velocities. Traveling at speeds of up to 60,000 miles per hour, these tiny particles strike the surface with immense energy, creating microscopic craters and breaking down rocks into finer particles. Their constant bombardment has effectively turned the Moon's surface into a dynamic, ever-changing environment, even on a microscopic scale. The absence of an atmosphere not only allows meteoroids to strike the Moon directly, but also amplifies their effects. On Earth, friction with the atmosphere causes most meteoroids to burn up before reaching the ground. On the Moon, however, there is no such protection. Every meteoroid, no matter how small, impacts with its full force, leaving a mark on the surface. Some of the most dramatic examples of meteoroid impacts can be found in the Moon's bright ray systems. These are created when material from an impact is ejected in long, straight lines, radiating outward from the crater. The Tycho crater, with its prominent rays extending over 1,500 miles, is a prime example. These features not only highlight the power of meteoroid impacts, but also provide scientists with clues about the age and composition of the Moon's surface. The continuous bombardment of meteoroids has significant implications for future lunar exploration. For one, it emphasizes the need for durable materials and robust designs for habitats and equipment. Structures must be able to withstand both the physical impacts of meteoroids and the abrasive effects of regolith. Protective measures, such as shielding and redundant systems, will be essential for ensuring the safety of both humans and machinery on the Moon. Additionally, studying the impacts of meteoroids provides valuable insights into the history of the solar system. Each crater, from the smallest pit to the largest basin, represents a snapshot of a specific event in time. By analyzing these features, scientists can better understand the dynamics of celestial collisions, the distribution of impactors in the solar system, and the processes that shape planetary surfaces. The Moon's surface, scarred and pitted by billions of years of impacts, stands as a reminder of the relentless forces at work in the cosmos. It tells a story of creation and destruction, of chaos and order. As we prepare for the next era of lunar exploration, understanding the role of meteoroids will be crucial in navigating the challenges and unlocking the mysteries of the Moon. The craters, basins, and ejecta fields are not just obstacles. They are windows into the history of our solar system, waiting to be explored. The Apollo program stands as one of humanity's most remarkable achievements. It was a daring endeavor, fueled by a race to the Moon and a quest for knowledge that forever changed our understanding of the cosmos. Between 1969 and 1972, 6 Apollo missions successfully landed on the lunar surface, with each mission uncovering groundbreaking discoveries that continue to shape our perspective on the Moon. These missions were not only a testament to human ingenuity, but also pivotal in revealing the mysteries of Earth's closest celestial neighbor. The Apollo program began with a vision: to send humans to the Moon and bring them back safely. President John F. Kennedy's bold proclamation in 1961 set the stage for what would become an unprecedented feat of science and engineering. But more than a political or technological challenge, Apollo represented an opportunity to transform the Moon from a distant, mysterious object into a tangible and scientifically rich world. Apollo 11, the first successful lunar landing, marked a historic milestone. On July 20th, 1969, Neil Armstrong and Buzz Aldrin became the first humans to set foot on the Moon, with Michael Collins piloting the command module in orbit. The images of Armstrong's giant leap for mankind captured the imagination of billions. Yet, beyond the symbolism, Apollo 11's primary mission was to conduct scientific experiments and collect samples of lunar material. The mission returned 47 pounds, 21.5 kilograms, of rocks and soil, providing scientists with their first direct look at the moon's composition. These samples revealed that the moon's surface was covered in regolith, a fine, powdery dust formed by billions of years of meteoroid impacts. Analysis showed that the moon was geologically distinct from Earth, with its rocks containing no water and exhibiting signs of ancient volcanic activity. Perhaps most importantly, the Apollo 11 samples provided the first evidence supporting the giant impact hypothesis. The theory that the moon was formed when a Mars-sized object collided with Earth early in its history. Following Apollo 11, each subsequent mission expanded the boundaries of exploration. Apollo 12, landing just a few months later, demonstrated improved precision landing techniques, enabling the astronauts to explore specific scientific targets. The crew collected samples from a previously landed robotic probe, the Surveyor 3, allowing scientists to study the effects of long-term exposure to the lunar environment. Apollo 14 in 1971 brought a renewed focus on lunar geology. The mission explored the Fra Mauro Highlands, a region believed to contain material from deep within the moon's crust, ejected by an ancient impact event. The astronauts, Alan Shepard and Edgar Mitchell, used advanced tools like the Modular Equipment Transporter, a small, two-wheeled cart, to carry their instruments and samples. This mission not only provided a greater variety of lunar materials, but also refined techniques for working in the moon's unique environment. Apollo 15 marked a turning point in lunar exploration. It was the first mission to include the Lunar Roving Vehicle, LRV, a battery-powered rover that allowed astronauts to travel farther from the landing site. This mobility revolutionized the ability to explore and conduct scientific experiments on the moon. The Apollo 15 crew studied the Hadley Rill, a sinuous valley believed to have formed from ancient lava flows. The mission collected more than 170 pounds, 77 kilograms, of rocks and soil, including samples of anorthosite, a type of rock that revealed insights into the moon's crust formation. Apollo 16 and Apollo 17 pushed the boundaries even further. Apollo 16 explored the Descartes Highlands, a region of higher elevation and older terrain, while Apollo 17 focused on the Taurus-Littrow Valley, known for its diverse geological features. Apollo 17, the final mission, also included the first scientist astronaut, geologist Harrison Schmitt, who played a crucial role in identifying and collecting scientifically significant samples. Together, the Apollo missions returned over 800 pounds, 382 kilograms, of lunar material, which continues to be studied decades later. These samples have provided invaluable insights into the moon's history, including its volcanic activity, crust formation, and interactions with meteoroids. They have also helped refine our understanding of the early solar system, offering clues about the processes that shaped planetary bodies. Beyond the scientific achievements, the Apollo missions paved the way for advancements in technology and engineering. The knowledge gained from designing life support systems, spacecraft, and navigation tools laid the foundation for modern space exploration. Techniques developed during Apollo have been adapted for robotic missions, satellites, and even plans for future human exploration of Mars. The legacy of the Apollo program extends far beyond the scientific community. It inspired generations to dream of the stars and demonstrated the power of collaboration and determination. The images of astronauts walking on the moon, Earth rising above the lunar horizon, and the stark beauty of the moon's surface remain some of the most iconic symbols of human achievement. As we look toward the future of lunar exploration, the Apollo missions serve as a reminder of what is possible when humanity comes together in pursuit of knowledge. They were the first steps in a journey that continues to unfold, providing the foundation for new missions such as NASA's Artemis program, which aims to return humans to the moon and establish a sustainable presence. The discoveries made by Apollo are not just relics of the past. They are the building blocks of our future in space. Since the Apollo program, humanity's exploration of the moon has shifted from fleeting visits to a vision of long-term presence and scientific inquiry. Modern lunar missions, driven by advancements in technology and international collaboration, are expanding our understanding of the moon and laying the groundwork for future exploration. From orbiters mapping the lunar surface in unprecedented detail to landers and rovers conducting sophisticated experiments, these missions are transforming our knowledge of the moon and its potential. One of the most significant milestones in modern lunar exploration was the launch of the Lunar Reconnaissance Orbiter, LRO, by NASA in 2009. This mission aimed to create detailed maps of the moon's surface, providing high-resolution images and 3D topographic data. The LRO's findings have revolutionized our understanding of the moon's geography, revealing hidden craters, identifying potential landing sites, and mapping regions of water ice near the poles. Its observations have also confirmed the presence of permanently shadowed regions, some of the coldest places in the solar system, which could be key to sustaining human presence on the moon. In parallel, other nations have joined the effort to explore the moon. China's Chang'e program has been particularly impactful, with a series of missions that include orbiters, landers, and rovers. In 2013, Chang'e 3 marked a significant achievement by landing on the moon and deploying the U-2 rover, which conducted geological surveys and studied the moon's subsurface. Chang'e 4 followed in 2019, becoming the first mission to land on the far side of the moon. This groundbreaking mission explored a region of the moon that remains largely unstudied, providing new insights into its composition and the history of the solar system. India has also made significant contributions to lunar exploration through its Chandrayaan program. Chandrayaan-1, launched in 2008, played a pivotal role in confirming the presence of water molecules on the moon's surface. Its follow-up mission, Chandrayaan-2, included an orbiter, lander, and rover, aiming to study the moon's south pole. While the lander experienced challenges during descent, the orbiter continues to provide valuable data on the lunar surface and exosphere. Private companies have also entered the lunar exploration arena, spurred by commercial interest and the promise of resources like water ice and rare minerals. Firms such as SpaceX, Blue Origin, and Astrobotic are developing landers and rovers to support scientific research and infrastructure development on the moon. These efforts are not only accelerating technological advancements, but also highlighting the role of public-private partnerships in expanding the scope of space exploration. A key component of modern lunar missions is the search for resources that could support future human habitation. Water ice, detected in shadowed craters near the moon's poles, is a critical target. This resource could be used to produce drinking water, oxygen for breathing, and hydrogen for rocket fuel. Missions like NASA's VIPER, Volatiles Investigating Polar Exploration rover, set to launch in the near future, are designed to map the distribution of water ice and assess its usability. Such endeavors are essential for building a sustainable presence on the Moon and enabling deeper exploration into the solar system. The Artemis program, led by NASA in collaboration with international partners, represents a bold step forward in returning humans to the Moon. Artemis aims to establish a sustainable lunar presence by the end of the decade, focusing on the Moon's South Pole region. Artemis I, the program's uncrewed test flight, successfully demonstrated the capabilities of the Space Launch System, SLS, and the Orion spacecraft, paving the way for Artemis II, which will carry astronauts around the Moon. Ultimately, Artemis III will land the first woman and the next man on the lunar surface, marking a new chapter in human exploration. Central to the Artemis program is the development of the Lunar Gateway, a space station that will orbit the Moon and serve as a hub for future exploration. The Gateway will support extended missions, provide a platform for scientific research, and act as a staging point for travel to Mars and beyond. Its modular design, built with contributions from international partners, reflects the global nature of modern space exploration. Robotic missions continue to play a vital role in paving the way for human exploration. Landers like NASA's Commercial Lunar Payload Services, CLPS, aim to deliver scientific instruments and technology demonstrations to the Moon's surface. These missions are testing systems for navigation, communication, and resource utilization, ensuring that future human explorers have the tools they need to thrive in the lunar environment. Modern lunar exploration is also addressing critical questions about the Moon's origins and evolution. Instruments aboard recent missions are analyzing isotopes in lunar rocks, studying volcanic activity, and measuring the Moon's magnetic field. These findings are refining our understanding of how the Moon was formed and how it has changed over billions of years. As humanity sets its sights on returning to the Moon, the lessons learned from modern missions are shaping the future of space exploration. The innovations developed for lunar exploration, such as advanced robotics, autonomous systems, and sustainable resource utilization, will have far-reaching implications for missions to Mars and other celestial bodies. The renewed focus on the Moon underscores its importance as both a scientific destination and a stepping stone for deeper space exploration. The efforts of nations, private companies, and international collaborations are laying the groundwork for a new era of exploration, one that seeks not only to understand the Moon, but to use it as a launch pad for humanity's journey into the cosmos. Modern missions are not just about revisiting the Moon. They are about unlocking its potential and expanding the horizons of human knowledge and ambition. Exploring the Moon has never been an easy endeavor. It is a tale of perseverance, human ingenuity, and the courage to face the unknown. From the early Apollo missions to modern exploration efforts, astronauts, engineers, and scientists have faced countless challenges on their journey to unlock the secrets of the Moon. These stories, both triumphant and harrowing, reveal the incredible lengths humanity has gone to in its quest for lunar knowledge. One of the most iconic moments of perseverance in lunar exploration occurred during the Apollo 13 mission. What began as a routine trip to the Moon turned into a life-or-death struggle when an oxygen tank exploded, crippling the spacecraft. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, worked closely with mission control to improvise solutions, including building a makeshift carbon dioxide filter using duct tape and other onboard materials. Against all odds, the astronauts returned safely to Earth. While Apollo 13 never landed on the Moon, its story is a testament to human resourcefulness and the importance of teamwork under pressure. In the years that followed, other missions faced challenges that highlighted the unpredictable nature of lunar exploration. During Apollo 12, for instance, the mission was nearly aborted before it even began. Moments after launch, the spacecraft was struck by lightning, temporarily disabling its systems. Quick thinking by the crew and ground control restored power, allowing the mission to proceed. Apollo 12 ultimately became a successful mission, landing in the ocean of storms and collecting vital scientific data. Modern missions have also encountered their share of hurdles. Chandrayaan-2, India's ambitious mission to explore the Moon's south pole, faced a setback when its Vikram lander lost communication during descent. While the orbiter continues to provide valuable data, the loss of the lander was a sobering reminder of the complexities involved in soft landing on the lunar surface. Similarly, Israel's Bereshit mission, a private endeavor to land on the Moon, ended in failure when the spacecraft crashed during its final descent. Despite these challenges, both missions have inspired further innovation and determination to achieve success in future attempts. The Moon's extreme environment poses significant challenges for exploration. Astronauts navigating the lunar surface during the Apollo missions faced issues with regolith, the fine dust that covers the Moon. Regolith clung to their suits, scratched their visors, and even damaged seals on equipment. During Apollo 17, astronaut Gene Cernan experienced a broken fender on the lunar roving vehicle, causing dust to spray over the rover and complicating their activities. In a clever display of improvisation, the crew repaired the fender using duct tape and maps, ensuring the mission could continue. Technological challenges have also been a defining feature of lunar exploration. Designing equipment that can withstand the Moon's temperature extremes, radiation, and lack of atmosphere has required groundbreaking innovation. The lunar module, for example, was a masterpiece of engineering, capable of landing on the Moon's surface with pinpoint accuracy and then launching astronauts back into orbit. Similarly, modern rovers and instruments must operate autonomously in an environment where communication delays and harsh conditions leave little room for error. One of the most inspiring stories of perseverance comes from the Chang'e 4 mission, which successfully landed on the Moon's far side in 2019. This mission required overcoming significant technical hurdles, including developing a relay satellite to enable communication with Earth. The success of Chang'e 4 has opened new opportunities to study the Moon's far side, an area shielded from Earth's radio interference and rich in scientific potential. Human perseverance in lunar exploration is not limited to overcoming technical challenges. It also extends to the physical and mental endurance of astronauts. Lunar missions demand extensive training, including simulations of zero gravity and isolation, to prepare for the psychological toll of space travel. Astronauts must also adapt to the Moon's reduced gravity, which affects movement and coordination, making even simple tasks more complex. The pursuit of lunar exploration has also inspired international collaboration, fostering a sense of shared purpose. The Artemis program, for example, involves contributions from numerous countries and private companies, highlighting the importance of cooperation in achieving ambitious goals. This collective effort ensures that future challenges are met with the combined expertise and resources of a global community. Despite the obstacles, each mission, whether a triumph or a setback, adds to humanity's growing knowledge of the moon. These stories of perseverance remind us that exploration is a journey, one that requires resilience, creativity, and an unyielding desire to push beyond our limits. The challenges faced by past and present missions serve as valuable lessons, guiding future explorers as they prepare to return to the moon and venture even farther into the cosmos. As we reflect on these stories, we are reminded of the profound connection between exploration and the human spirit. The moon, with its challenges and mysteries, continues to inspire us to strive for greatness. Each mission is a chapter in a story that is far from over, a story that will continue to unfold as humanity reaches for the stars. The moon, Earth's closest celestial neighbor, has fascinated humanity for millennia. From ancient myths to scientific discoveries, it has been a constant source of curiosity. Yet, despite the countless missions and advancements in technology, the moon continues to harbor mysteries. Some of its phenomena remain unexplained, challenging our understanding of planetary science and leaving us with questions that demand answers. This section delves into some of the most puzzling and captivating phenomena observed on the moon. One of the most enigmatic phenomena associated with the moon is the occurrence of transient lunar phenomena, TLP. These are short-lived flashes, glows, or color changes on the lunar surface that have been reported for centuries. First documented by astronomers in the 1700s, TLP events remain a subject of debate and intrigue. They can appear as sudden bursts of light, glowing patches, or even areas that seem to darken temporarily. The causes of TLP are still unknown, but scientists have proposed several theories. One possibility is that these phenomena are caused by outgassing, where volatile gases trapped beneath the moon's surface are released through fissures, creating visible changes. Another hypothesis suggests that TLP may result from meteorite impacts, which could produce brief flashes of light as they strike the lunar surface. Alternatively, interactions between the moon's surface and charged particles from the solar wind might also contribute to these occurrences. Despite numerous observations, TLP remains elusive. With advancements in lunar observation technology, including orbiters and high-resolution telescopes, scientists hope to capture definitive evidence of these events. If confirmed, studying TLP could provide insights into the moon's geological activity and its interaction with the space environment. The far side of the moon, often referred to as the dark side, is another area shrouded in mystery. While it is not actually dark, receiving the same amount of sunlight as the near side, it remains hidden from Earth due to tidal locking. This constant orientation has made the far side an intriguing yet challenging target for exploration. One of the most significant discoveries about the far side is the South Pole Aitken Basin, the largest known impact crater in the solar system. Stretching over 1,600 miles in diameter and reaching depths of up to 8 miles, this basin is a geological marvel. However, recent studies using data from the Lunar Reconnaissance Orbiter and China's Chang'e 4 mission have revealed an unexpected anomaly beneath this basin. A massive, dense structure buried under the surface. This anomaly, often referred to as a metallic mass, is thought to weigh billions of tons. Scientists hypothesize that it could be remnants of the asteroid that created the basin, or perhaps material from the moon's mantle brought up during the impact. Another theory suggests that the mass might be a concentration of metal oxides formed during the moon's early cooling period. Regardless of its origin, the anomaly raises fascinating questions about the Moon's formation and evolution. Unlike Earth, the Moon lacks a global magnetic field. However, localized magnetic anomalies have been detected on its surface, baffling scientists. These regions, known as lunar swirls, appear as bright, sinuous patterns on the Moon's surface. Some of the most notable examples include the Reiner Gamma swirl and similar formations in Mare Ingeni and Mare Marginis. What makes these swirls particularly intriguing is their strong association with localized magnetic fields. Lunar swirls are often found in areas where the surface is shielded from solar wind particles, suggesting that the magnetic fields may be deflecting the solar wind and preserving the brightness of the terrain. However, the origin of these magnetic anomalies remains uncertain. One theory posits that they could be remnants of ancient magnetic fields generated during the Moon's early history. Another suggests that they may have been caused by cometary impacts, which could have deposited magnetic material on the surface. Studying these anomalies offers a unique opportunity to explore the Moon's ancient past and understand how magnetic fields evolve on planetary bodies. It also has practical implications for future lunar missions, as localized magnetic fields could affect navigation and equipment operation. The discovery of water ice on the Moon has been one of the most groundbreaking findings in recent decades. Using data from missions like India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter, scientists have identified significant deposits of water ice in permanently shadowed craters near the Moon's poles. These regions, shielded from sunlight for billions of years, create conditions where ice can remain stable. While the presence of water ice is a remarkable discovery, its origin remains a mystery. One possibility is that the ice was delivered by comets and asteroids during impacts. Another theory suggests that water molecules could form through chemical reactions between solar wind particles and oxygen-bearing minerals on the Moon's surface. Understanding how this ice formed and how it is distributed is critical for future lunar exploration, as it could serve as a resource for drinking water, oxygen production, and rocket fuel. The exploration of these shadowed regions poses significant challenges due to their extreme cold and lack of sunlight. However, upcoming missions like NASA's VIPER rover aim to map these ice deposits in greater detail, unlocking the potential for sustained human presence on the Moon. The Moon has also been the site of unexplained signals and observations that continue to spark curiosity. For example, during the Apollo missions, astronauts reported strange flashes of light when their eyes were closed. Known as cosmic ray flashes, these events are thought to be caused by high-energy particles striking the retina. While not unique to the Moon, these flashes highlight the challenges of operating in an environment with intense cosmic radiation. Another curious observation involves the so-called moonquakes. Unlike earthquakes, which are caused by tectonic activity, moonquakes are believed to result from various factors, including thermal expansion, meteorite impacts, and gravitational interactions with Earth. Some moonquakes occur at depths of several hundred kilometers, raising questions about the Moon's internal structure and whether it still retains some level of geological activity. Additionally, some radio signals detected near the Moon have sparked debates about their origin. While most can be attributed to natural sources, such as solar emissions or interactions between the solar wind and the lunar surface, a small number remain unexplained. These anomalies continue to intrigue scientists and fuel speculation about the Moon's unexplored mysteries. The moon's phenomena are not just curiosities. They hold the key to understanding broader questions about the solar system's history. Its surface serves as a natural archive, preserving evidence of cosmic events that have shaped the inner planets. Craters, for instance, reveal patterns of asteroid and comet impacts, while isotopic analysis of lunar rocks offers clues about the early solar system's composition. Unraveling the moon's mysteries also has implications for future exploration. Understanding the processes behind TLP, magnetic anomalies, and water ice formation could inform missions to other celestial bodies, such as Mars or Europa. Moreover, studying the moon's geology and environment helps refine the technologies needed for long-duration space travel and habitation. The unexplained phenomena on the moon remind us that even our closest neighbor in space holds countless secrets. Each discovery, from transient flashes to buried metallic masses, expands our understanding of not just the moon, but the fundamental processes shaping the universe. These mysteries challenge us to look deeper, think critically, and push the boundaries of exploration. The moon has always been a source of wonder, but its enigmatic nature has also posed scientific challenges that continue to inspire inquiry. Over the decades, countless theories have emerged to explain the mysteries of the moon, from its origin to its unique phenomena. These theories not only attempt to answer lingering questions about our nearest celestial neighbor, but also broaden our understanding of planetary science and the early history of the solar system. The most widely accepted explanation for the moon's formation is the giant impact hypothesis. This theory suggests that approximately 4.5 billion years ago, a Mars-sized protoplanet called Theia collided with the young Earth. The catastrophic impact ejected a massive amount of material into orbit, which eventually coalesced to form the moon. This hypothesis explains many of the moon's characteristics, including its size, density, and composition, which closely resemble Earth's mantle. However, recent isotopic analyses of lunar rocks have complicated this narrative. These studies reveal that the Moon and Earth share nearly identical isotopic signatures, suggesting that their material came from the same source. If Theia contributed significantly to the Moon's formation, why don't we see a distinct isotopic difference? This conundrum has led to alternative theories, such as a high-energy collision that vaporized Theia and Earth's outer layers, mixing their materials before forming the Moon. Another theory posits that the Moon might have formed from a series of smaller impacts rather than a single cataclysmic event. This multiple impact hypothesis offers an intriguing perspective on how celestial collisions shaped the early solar system, but it remains less widely supported than the giant impact hypothesis. One of the Moon's most perplexing mysteries is the presence of magnetic anomalies. Unlike Earth, which has a global magnetic field generated by its liquid outer core, the Moon's magnetic field is localized and patchy. These regions, known as lunar swirls, appear as bright, sinuous patterns on the surface, with the Reiner Gamma formation being one of the most notable examples. Theories about these magnetic anomalies vary. One hypothesis suggests that they are remnants of an ancient lunar dynamo, a mechanism similar to Earth's core that generated a magnetic field in the Moon's early history. As the Moon cooled and its core solidified, this dynamo ceased, leaving behind localized fields in areas where magnetic materials were concentrated. Another theory links lunar swirls to cometary impacts. Comets, rich in volatile materials, could have deposited magnetic particles on the surface during high-velocity collisions, creating the swirls we see today. These features' alignment with magnetic anomalies suggests a strong relationship between the surface's appearance and its magnetic properties, but the exact mechanisms remain unclear. Understanding these anomalies not only sheds light on the Moon's magnetic history, but also provides a window into the processes that govern planetary magnetism. Future missions equipped with advanced magnetometers could help unravel the origins of these intriguing patterns. The discovery of water ice in permanently shadowed craters near the lunar poles has revolutionized our understanding of the Moon. This ice is thought to have been preserved for billions of years in regions that never receive sunlight, where temperatures can plunge to minus 250 degrees Fahrenheit. However, the origins of this ice remain a subject of debate. One theory suggests that the ice was delivered by comets and asteroids, which deposited water molecules during impacts. Another hypothesis posits that solar wind particles interacting with oxygen-rich minerals on the lunar surface could have produced water through chemical reactions. This process, while less efficient, could explain the presence of ice in regions not directly impacted by comets or asteroids. The distribution of water ice also raises questions. Why is it more concentrated in some craters than others? Is the ice mixed with regolith, or does it exist in pure layers? Missions like NASA's VIPER rover aim to answer these questions by mapping and analyzing the ice deposits, which could serve as critical resources for future lunar colonies. Transient lunar phenomena, TLP, are one of the Moon's most enduring enigmas. These fleeting events, which include sudden flashes of light, glowing patches, or temporary darkening of the surface, have been reported for centuries. Despite numerous accounts, TLP remains elusive and poorly understood. One plausible explanation for TLP is outgassing, where volatile gases trapped beneath the surface are released through cracks or fissures. This release could produce visible effects, particularly in areas with concentrated geological activity. Another possibility is that TLP results from meteorite impacts, which create brief, intense flashes upon striking the lunar surface. A more speculative theory involves electrostatic activity. The Moon's lack of atmosphere allows the solar wind to directly interact with the surface, potentially creating localized electric discharges that manifest as TLP. Observing these phenomena in real time is challenging, but advances in telescopic and orbital imaging may soon provide clearer evidence. While the Moon is often considered geologically dead, the existence of moonquakes suggests otherwise. These seismic events, detected by instruments left behind during the Apollo missions, occur in several forms: thermal, impact-related, and deep moonquakes originating hundreds of kilometers below the surface. Deep moonquakes are particularly intriguing because they imply the presence of residual geological activity. Some scientists theorize that tidal forces from Earth's gravitational pull create stresses within the Moon, triggering these quakes. Others suggest that slow cooling and contraction of the Moon's interior may also play a role. The implications of moonquakes extend beyond academic curiosity. Understanding their causes and frequency is essential for designing lunar habitats and infrastructure capable of withstanding seismic events. Future missions with advanced seismometers could refine our understanding of the Moon's internal structure and its ongoing evolution. The discovery of a massive, dense structure beneath the South Pole Aitken Basin on the Moon's far side has sparked significant scientific interest. This anomaly, detected through gravity mapping and radar data, is thought to weigh billions of tons, but its origin remains uncertain. One hypothesis suggests that the anomaly is the remains of the asteroid that created the basin. The impact could have embedded metallic fragments deep within the lunar crust. Another possibility is that the structure is composed of materials from the Moon's mantle, brought to the surface during the collision. Alternatively, The anomaly might represent an unusually high concentration of oxides formed during the Moon's early differentiation. Studying this structure could provide crucial insights into the processes that shaped the Moon's interior and the solar system's history. Theories about the Moon's mysteries extend beyond its surface. They inform our understanding of planetary formation, magnetic field evolution, and the distribution of water and volatiles across the solar system. For example, insights gained from studying lunar water ice could be applied to other celestial bodies, such as Mars or Europa, where similar processes might occur. The Moon's magnetic anomalies and swirls offer a natural laboratory for studying how localized magnetic fields interact with the solar wind, a phenomenon relevant to space weather research. Similarly, investigating the Moon's seismic activity and subsurface structures helps refine models of planetary geology and tectonics. The Moon's mysteries are a reminder of how much we still have to learn, even about our closest celestial neighbor. Each theory, whether about its formation, magnetic anomalies, or water ice, represents a step toward unlocking the secrets of the Moon, and, by extension, the history of the solar system. As new missions venture to the lunar surface and advanced technologies provide more data, the answers to these enduring questions may finally come into focus. The Moon, with all its mysteries, continues to inspire humanity to explore, question, and discover. As humanity sets its sights on returning to the Moon, the idea of building a permanent lunar base has moved from the realm of science fiction into tangible reality. The vision of establishing a sustainable presence on the Moon is no longer a distant dream. It is a strategic goal that underpins modern lunar exploration programs like Artemis and international collaborations. A lunar base would serve as a cornerstone for scientific discovery, technological innovation, and a stepping stone for missions deeper into the solar system. The concept of a lunar base begins with location. Scientists and engineers have identified the Moon's south pole as one of the most promising sites for such a venture. This region holds significant advantages, primarily the presence of permanently shadowed craters containing water ice. These ice deposits are invaluable, as they can be converted into water for drinking, oxygen for breathing, and hydrogen for rocket fuel. The South Pole's elevated regions also receive nearly constant sunlight, making them ideal for solar power generation, a crucial factor for sustaining a long-term presence on the Moon. Designing a lunar base requires overcoming a unique set of challenges. The Moon's environment is harsh and unforgiving, with extreme temperature fluctuations, high radiation levels, and a surface covered in abrasive regolith. These conditions necessitate innovative solutions for habitats, power systems, and life support infrastructure. One proposed approach involves using regolith as a building material, either through 3D printing or sintering techniques. By utilizing resources available on the Moon, this strategy reduces the need to transport materials from Earth, significantly lowering costs. Power generation is another critical aspect of a lunar base. Solar power is the most viable option, particularly in regions with extended sunlight. Solar arrays could provide energy for habitats, research stations, and mining operations. To address periods of darkness, energy storage systems, such as advanced batteries or regenerative fuel cells, would be essential. Some proposals even suggest using small modular nuclear reactors as a reliable backup power source. Radiation shielding is a top priority for ensuring the safety of astronauts. Without an atmosphere or magnetic field, the Moon is exposed to harmful cosmic rays and solar radiation. Habitats would need to incorporate shielding, either by covering structures with regolith or constructing them underground. These measures would protect astronauts from long-term exposure and reduce health risks associated with radiation. Life support systems represent another critical challenge. A lunar base must sustain its inhabitants by recycling air, water, and waste. Advanced closed-loop systems, similar to those tested on the International Space Station, would be adapted for use on the Moon. These systems would allow for efficient resource management, minimizing reliance on resupply missions from Earth. A lunar base would also serve as a hub for scientific research. The Moon offers a unique vantage point for studying the solar system and beyond. Its lack of atmosphere and stable surface make it an ideal location for astronomical observatories, including radio telescopes shielded from Earth's radio interference. Scientists could also study the Moon's geology, composition, and history to gain insights into planetary formation and the early solar system. Moreover, a lunar base could facilitate experiments in resource utilization, robotics, and human resilience in space. For instance, mining operations could extract water ice and other valuable resources, testing technologies that might one day be used on Mars. Robotic systems would play a key role in constructing and maintaining the base, as well as conducting exploration missions in hazardous environments. The establishment of a lunar base is not just about science and technology. It also has profound implications for humanity's future. A permanent presence on the Moon would symbolize humanity's ability to adapt and thrive beyond Earth. It would inspire generations to dream big, pursue careers in science and engineering, and collaborate across borders to achieve shared goals. International collaboration will be critical to the success of a lunar base. Programs like Artemis, spearheaded by NASA, already involve partnerships with agencies from around the world. Countries such as Canada, Japan, and members of the European Space Agency are contributing technology, expertise, and funding to make this vision a reality. Private companies are also playing a pivotal role, developing innovative solutions for transportation, habitats, and resource utilization. This collaborative approach not only distributes the financial and technical burden, but also fosters a sense of unity in the pursuit of exploration. The lessons learned from building and operating a lunar base will pave the way for future missions to Mars and beyond. The Moon serves as a proving ground, where technologies can be tested and refined in a relatively close and accessible environment. Success on the Moon would provide the confidence and experience needed to tackle the challenges of deeper space exploration, including the establishment of a base on Mars. In conclusion, the vision of a lunar base represents a monumental step forward for humanity. It is a testament to our ingenuity, resilience, and determination to explore the unknown. By establishing a sustainable presence on the Moon, we are not only unlocking the mysteries of our nearest celestial neighbor, but also laying the foundation for humanity's future as a spacefaring species. The journey to the Moon is no longer just about reaching its surface. It is about staying, thriving, and using the Moon as a gateway to the stars. The Moon, long seen as a barren wasteland, is now emerging as a treasure trove of resources that could revolutionize space exploration. From water ice hidden in permanently shadowed craters to vast reserves of rare minerals, the Moon's resources hold the potential to support sustainable human habitation and serve as a launchpad for deeper space missions. Harnessing these resources isn't just about survival. It's about transforming how humanity explores and thrives beyond Earth. One of the most critical resources on the Moon is water ice, discovered in the permanently shadowed regions near its poles. These deposits are invaluable for several reasons. First, water is essential for human survival, and extracting it from the moon eliminates the need for costly transport from Earth. Second, water can be broken down into hydrogen and oxygen through electrolysis, providing both breathable air and rocket fuel. This process, known as in situ resource utilization, ISRU, is key to reducing the costs and logistical challenges of space exploration. The significance of water ice extends beyond immediate human needs. Hydrogen produced from lunar ice could power rockets for missions to Mars and beyond, establishing the Moon as a refueling station for interplanetary travel. The ability to mine, process, and utilize this resource would represent a paradigm shift in space exploration, enabling long-term missions that were previously considered impossible. Extracting water ice, however, poses challenges. The regions where ice exists are some of the Moon's most inhospitable areas, with temperatures plunging below -250 degrees Fahrenheit. Specialized robotic systems will be required to operate in these extreme conditions, mining and transporting ice for processing. Upcoming missions like NASA's VIPER rover aim to map and analyze these deposits, paving the way for large-scale extraction in the future. The Moon's surface is covered in a fine, powdery substance known as regolith. At first glance, it might seem like an obstacle, given its abrasive nature and tendency to cling to everything. However, regolith is increasingly being seen as a valuable resource. It contains a variety of elements, including oxygen, silicon, and iron, that could be extracted for use in building materials and life support systems. One of the most promising uses of regolith is in construction. Techniques like 3D printing could transform lunar regolith into bricks, tiles, or even entire habitats. This approach, known as additive manufacturing, reduces reliance on Earth-based materials and enables the construction of infrastructure directly on the Moon. Regolith could also be melted and solidified into glass for windows or radiation shielding, further enhancing the self-sufficiency of lunar bases. Moreover, regolith contains helium-3, a rare isotope that holds potential as a fuel for future nuclear fusion reactors. While the technology to harness helium-3 for energy production is still in its infancy, its presence on the Moon underscores the potential of lunar resources to drive innovation not just in space, but on Earth as well. The Moon is believed to contain deposits of rare earth elements, REEs, and other valuable minerals. These materials are essential for manufacturing electronics, renewable energy systems, and advanced technologies. While Earth has significant REE reserves, mining them is often environmentally damaging and geopolitically sensitive. Lunar mining could provide an alternative source, reducing dependence on terrestrial extraction and contributing to sustainable development. However, mining on the Moon presents unique challenges. The lack of atmosphere means there is no protection from micrometeoroids, radiation, or temperature extremes, all of which can damage equipment. Additionally, the low-gravity environment requires innovative mining techniques to efficiently extract and transport materials. Robotic systems, autonomous vehicles, and advanced sensors will play a crucial role in overcoming these obstacles. The Moon offers opportunities for energy production that could support both lunar operations and missions beyond. Solar power is the most viable energy source, especially in regions near the poles where sunlight is abundant for extended periods. Solar panels can be deployed to generate electricity for habitats, mining equipment, and scientific instruments. Excess energy can be stored in batteries or converted into hydrogen through water electrolysis, creating a renewable energy cycle. In addition to solar power, the potential for nuclear energy on the Moon is being explored. Compact nuclear reactors, such as NASA's Kyla Power project, could provide a reliable and consistent energy source, particularly during the long lunar nights. While the potential benefits of harnessing lunar resources are immense, the process raises significant challenges and ethical questions. Mining operations must be designed to minimize their environmental impact on the Moon's surface, preserving its scientific and cultural value. Harnessing the Moon's resources is not just a technical challenge. It is a pivotal step toward humanity's future in space. The Moon has always been a symbol of mystery, inspiration, and aspiration. Its silver glow has guided sailors, inspired poets, and driven scientific curiosity for centuries. Today, it stands at the forefront of humanity's quest to become a spacefaring civilization. As we embark on a new era of lunar exploration, the Moon is no longer just a celestial body to observe from afar. It is a destination, a resource, and a gateway to the stars. The Moon also serves as a stepping stone for humanity's broader ambitions in space. It is a proving ground for technologies, systems, and strategies that will be critical for missions to Mars and beyond. The lessons we learn on the Moon, how to live, work, and innovate in a hostile environment, will shape the future of interplanetary exploration. It is here that we will build the foundation for a human presence across the solar system. The Moon's mysteries remind us that there is still so much to discover. Its challenges inspire us to innovate, and its opportunities push us to dream bigger. Each mission, each step on its surface, brings us closer to answering the fundamental questions of existence. Where did we come from? Are we alone? And what lies ahead for humanity in the cosmos? The Moon is more than just a destination. It is a symbol of human potential. It teaches us to reach for the stars while staying grounded in our shared humanity. As we return to the Moon and envision a future among the planets, we carry with us the spirit of exploration that has driven progress for centuries. The Moon is calling us, not just to explore, but to stay, to learn, and to build a future that extends beyond the boundaries of Earth. It is the next frontier, a frontier that promises to transform how we understand ourselves, our planet, and our place in the universe. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.